Hello students, myself Antara Ghoshal, Assistant Professor of EC Department of Guru Nanak Institute of Technology. This is my lecture series on RF and Microwave Engineering, and the subject code is EC701. The subject name is RF and Microwave Engineering, and the course code is EC701, and the total lectures for this course are 34. There are some course objectives. Now, what are the course objective of this subject? First one is distinguish the RF and microwave spectrum, planar transmission lines, and high frequency circuit elements. Second one is determine the microwave passive components and scattering matrix representation. Third one is illustrate the microwave tubes, semiconductor microwave devices. And the fourth one is justify the microwave application and typical microwave test bench. These four are the course objectives of this subject course. Now, after completion of this course, the students will be able to understand the microwave frequency range and their application. Also, they will be able to develop fundamental understanding of the two-port RF network and matching techniques. Also, they will be able to learn the scattering matrix for microwave passive components. Also understand the microwave tubes and devices along with their fundamental principles of operation. And the last one is learn the microwave measurement techniques. All these points are these are course outcome of this course. Now there are four modules. In first module there are introduction, RF and microwave spectrum, typical application of RF and microwave means radar and missile, safety consideration of RF and microwave. Now, in the previous class or lecture, I have introduced what is RF and microwave, what are the RF and microwave spectrum, and what are the different types of frequency band, and what are the range of those bands. Also, I have discussed about the application of RF and microwave like radar, and I have also discussed about different topics on radar, that what is radar, how it works, and what is the application of this radar in different types of uh, different areas, and also the safety considerations of RF and microwave. Now, today we will discuss about that microwave waveguide and waveguide resonator, which is under module 1. And under this module 1 there are different topics on this microwave waveguide, that is the rectangular waveguide, and the design consideration of this rectangular waveguide, then TE and TA mode. T10 mode analysis, cutoff frequency, propagation constant, intrinsic wave impedance, phase and group velocity, power transmission, attenuation, waveguide excitation, wall current, introduction of circular waveguide, rectangular waveguide resonator design considerations, resonant frequency, Q factor, and excitation. Now, today we will discuss about a topic on this section, that is microwave waveguide. Generally, if the frequency of a signal or a particular band of signal is high, the bandwidth utilization is high as the signal provides more space for the other signals to get accommodated. But the high frequency signals can't travel long distances without getting attenuated. Now, what is a microwave waveguide? That microwaves propagate through microwave circuits, components, and devices, which acts as a part of microwave transmission line, that is called as waveguides. A hollow metallic tube of uniform cross-section for transmitting electromagnetic waves by successive reflection from the inner walls of the tube is called waveguide. Now, what is the need of waveguide? Now, an electromagnetic wave at frequency, those electromagnetic waves at frequencies greater than 3 gigahertz, that electromagnetic wave transmission through cables become difficult, because this is due to the losses in the solid cable and the dielectric used to support the cable. For that, we use waveguide, which is a hollow metallic tube. Now, there are some basic features of this waveguide. Now, waveguides are used to carry energy from one equipment to another, like in an antenna transmitter power to antenna and mic transmitter power to antenna and micro signal from antenna to receiver. Now, waveguides are made of copper, aluminum, or brass, and these materials are extruded into long rectangular or circular pipes. The energy to be transmitted is injected from one end of the waveguide through probe, and the electric and the magnetic field of the signals bounce off the wall back and forth. All these are the basic features of waveguide. Now, these are the different types of waveguides. This is a rectangular waveguide, this is a circular waveguide, and this is a single raised waveguide. That is elliptical waveguide, and that is double raised waveguide. But in your syllabus, there are only rectangular waveguide and circular waveguide. Now, in this picture, You can see this is a rectangular waveguide and the dimension is A and B, and this is a circular waveguide with diameter D, and this is a picture of a circular waveguide, and that is the picture of a rectangular waveguide. Now, what are the application of this waveguide? Waveguide is an indispensable technology for all industries that make use of transmitting systems. Waveguides are used to transfer electromagnetic power efficiently from one point in space to another. These waveguides have high power handling capacity and a lower attenuation for a given cutoff wavelength. Now, these are the electromagnetic field configuration within the waveguide. And this electromagnetic field configuration that can be determined from Maxwell's equation, which you have already studied in your uh, previous course. In previous course of electromagnetic theory and transmission line, there you have already studied about Maxwell's equation. Here the electromagnetic field configuration can be determined from that Maxwell's equation, and there are number of configurations, and for this uh, electromagnetic field configuration there are different number of configurations, and each configuration is known as mode. And what are the possible modes? That transverse electromagnetic, that is TEM, transverse electric, that is TE, transverse magnetic field, that is TM, and hybrid mode. Now, let's start with what is transverse electromagnetic mode. Here, for transverse electromagnetic wave, that is TEM mode, electric and magnetic field components are transverse or perpendicular to the direction of the propagation. Here both electric and magnetic fields are directed components, that is Ez and Hz equal to 0. Now next one is transverse electric, that is TE wave. Here only the electric field is purely transverse. Only the electric field is purely transverse to the direction of propagation, and the magnetic field is not purely transverse. That is Ez and Hz, Ez equal to 0, but not but Hz not equal to 0. In the previous, that is in TM, there was Ez equal to 0 and Hz equal to 0. Here, for transverse electric, Ez equal to 0, but Hz not equal to 0. Next is transverse magnetic wave. Here, only magnetic field is transverse to the direction of propagation, and the electric field is not purely transverse. That means Ez not equal to 0, and hz equal to 0. Next is hybrid group. That is, here neither electric nor magnetic are clearly transverse to the direction of propagation. That means when Ez not equal to 0, Hz not equal to 0. Now, from this figure, we can see the components of electric and magnetic field. There are three directions, that is X, Y, and X, Y, and Z. And here E is the electric field and H is the magnetic field, and EX and HX are the according to x-axis, E Z and HZ is according to z-axis, and EY HY according to y-axis. Now in this picture the TE and TM mode operation is shown. Here in the in that portion, that is, this is a TE mode where means transverse electric, means the propagation in the direction of propagation. With the direction of propagation, the electric field is perpendicular to the direction of propagation. Now here the wave propagating in this direction. Here the blue part is the electric field. You can see that if the wave propagation in this direction and the electric field is perpendicular to that propagation to that direction of propagation, and this blue part is for electric field and the red part is for magnetic field. That here magnetic flux line, these lines, that is the magnetic flux lines, appear as a continuous loop. Now here in this figure shows the TM mode, that is transverse magnetic mode. Here the electric flux lines appear with beginning and end points. That blue line are the electric field and the red part is magnetic field. Now, as I have already told that there are different types of waveguides like rectangular, circular, and many other types of waveguides. Now, each waveguide has a dimension, and any shape of this cross section of a okay. Here this is a rectangular waveguide and this is a circular waveguide. Here any shape of the cross section of a waveguide can support electromagnetic waves, of which rectangular and circular waveguides have become more common. Now if a waveguide having rectangular cross section, that is called a rectangular waveguide. Now the dimensions of this the waveguide, which determines the operating frequency range. There are three steps, like the size of the waveguide that determines its operating frequency. Next, the frequency of operation is determined by the dimension A, which is usually made one half of the wavelength at lowest frequency of operation, and at cutoff frequency or below the cutoff frequency, the waveguide will not transmit energy. Now, in this figure, the wave paths in a waveguide at various frequencies is shown. When a probe launches energy into the waveguide, the electromagnetic fields bounce off the side. Here we can see that bounce of the side walls of the waveguide as shown in this diagram. Now, the angle of the incidence and reflection depend upon the operating frequency. At high frequency, the angles are large, and therefore the path between the opposite walls is relatively long. That path between the two opposite walls is relatively long. Then these two are at lower frequency, the angles decrease and the path between the sides shortens. Now, when the operating frequency reaches the cutoff frequency of the waveguide, the signal simply bounces back and forth directly between the side walls of the waveguide and has no forward motion. And at this cutoff frequency or below this cutoff frequency, no energy will propagate. Now there are different types of flexible waveguide. It is used for bends, twist, or in application where certain criteria may not be fulfilled by normal waveguides. And these figures show some of the flexible waveguides. This is a H bend waveguide, that is a E bend waveguide, and that is a twist waveguide. Now that's all for today, and you can see that today we have discussed about what is microwave waveguide, why we use waveguide, means what is the need of waveguide, and the basic features of a waveguide. I have already discussed about that, and there are different types of waveguides, that is a circular and rectangular waveguide, which is in your syllabus. And in next class we will discuss about rectangular waveguide in details, and this is the application of waveguide. And after that, there are different types of modes, and this is the figure of electric and magnetic field component. And the wave paths in a waveguide at varied frequencies, which is shown in this figure. There are four conditions when at high frequency, at medium frequency, at low frequency, and at cutoff frequency. And this is the flexible waveguide. These are the flexible waveguide. Now that's all for today. And if you have any query, you can mail me or contact me through my mobile number or mail ID. Thank you.